In continuing our discussion of thermodynamics, I think it pertinent that we further discuss Bernoulli's equation and how it relates to the general equation for an energy balance for any flow system. So I think it pertinent that we first start our discussion with what is the general energy balance for any flow system. And what do I mean even by flow system itself? Well, a flow system is that in which we have, say, some tank here, as such, and we have some sort of pipe in and some sort of pipe out of our tanker here, and we have some sort of fluid flowing in and some sort of fluid flowing out. Now, we can also have a number of things also occurring in this tank. For example, we could have some sort of initial liquid level. We could have some sort of stirrer in here, some sort of stir bar. We could be adding some sort of heat to it. Those are flames. Any of these things could be happening to our system here. But this is just a general diagram for some sort of flow system, okay? And what we want to do is we want to be able to relate the energy in this system. And we can do that kind of through thinking through the conservation of energy that was kind of taught in basic mechanics. So, in basic mechanics, you learned that some sort of energy for a system is going to be conserved, and the energies that we would talk about in this case would be the internal energy, U, and I'm going to make this specific to the mass of whatever fluid we are putting in and out of the system. So this is a specific internal energy, and then we would add to that our kinetic energy as well as our potential energy. And by taking the differential of this, we would, therefore, be finding the change in energy of our system. So let's figure this out a little bit further here. Kinetic energy, as we know, is going to be 1/2 times mass times velocity squared. Potential energy, at the same time, I'm going to call the difference in height between these two pipes, I'm going to call that Z, and you'll see why I'm not calling that H for height in a second. So this will be mass times our gravitational constant G times Z here. And again, we're looking at some sort of differential change, so this could be interpreted as the change in height between the two pipes. And then we're adding to that internal energy again, U. I said that was specific to the mass, so we would need to multiply by the mass to find the energy here. Now, in simplifying this side of the equation, we can really pull that m outside. We can factor out that mass here and be left with this equation. And now, what is our equivalence here? What can we set all of these things equal to? Well, I think it's obvious that in our initial equation we could say that the differential change in our energy is going to be equal to the energy coming into the system minus the energy going out of the system minus whatever energy is also consumed within that system. So I'm going to say the energy in minus the energy out minus the energy that is consumed within this system here. Now, the energy in, as you may be aware, is going to be completely reliant upon this tube here and how much fluid we are inputting into the system there. So that energy in, we can rewrite on this right side of the equation here. I'm actually going to draw a line here, and under this I'm going to do kind of another equal sign. This is supposed to denote the right side of this equation here. So, we can say that that's equal to the energy in, and the energy in will be, well, whatever our internal energy in is, plus the velocity coming in squared over 2 plus gravitational constant plus the height of the inlet tube. And all of that then is going to be multiplied by some differential change in mass in. Right? Similarly, well, actually, I guess this would be subtracted. We're going to have virtually the same thing for our outlet tube here. And honestly, I think we can take away these subscripts, as we've already denoted that in our term here, this differential mass going in term. So I'll go ahead and take away these subscripts as well, and we'll just write the differential change in mass going in on the outside of this. So we're subtracting this, and you can see the only really change between these two terms, the one on the left being energy in and the one on the right being energy out, is that there is a minus sign that will need to be distributed over the energy out. And this makes sense. Okay. Now, this is going to be the energy terms for this. However, there is also some sort of work that must be being done on the system by these two pipes, right? There is some sort of work happening here on our system, and this would be easier to show if the fluid level was higher, so I'll go ahead and make the fluid level higher. If the fluid level was somewhere about here, then we would have some sort of work occurring here as that fluid enters the system. So that's going to be work done on the system. And work done on the system has a positive term, as you remember from my last or previous video. And we said that is going to be equal to pressure times volume. Now, in this relationship between pressure and specific volume here, and that's what this is it's a specific volume term, meaning that it is related to the mass in some sense, we could then use the equivalence that rho is equal to mass divided by volume, and rewrite that as volume is equal to mass divided by rho. That's a rho. Now, using this equivalence, we could actually rewrite this PV term here as pressure over rho inside of our inlet function here. So it would have to be multiplied by some sort of change in mass going in. Similarly, we would have to subtract this exact same term, except this time it's going to be the mass going out. And again, this is just equating for the work that's happening at the inlet and outlet pipe due to whatever forces are acting there. So that's just accounting for that kind of pressure difference there. Okay, so we've accounted for everything really to do with the pipes in this system. Next, what we need to do is find some way in order to account for both the stirring and the heating of the system. Well, we can do this very simply. We can write this as plus the heat, the change in heat that has been entered into the system, that adds to an energy term in the first law equation, so we can do the same here, as well as I believe we can add the differential change of work, and we're going to call this non-flow work. This non-flow work is going to be things like stirring, things like shaking the container potentially, anything that doesn't, any work done on the system that isn't particularly relevant to or done by either of the two flow pipes. So now we have gone ahead and we have derived here, this is all one equation, we have derived here, and I'll highlight it in yellow, one energy balance. And this is the general energy balance for any flow system. So how can we go ahead and use this? Well, I think first what we need to do is simplify this to some extent. Let's go ahead and simplify this. What we can see is that in here, as well as here, these works associated with the injection flow, these also have the derivative of mass term, meaning we can put them inside the parentheses with the rest of the energy terms. So let's go ahead and do that. And I'm going to put it right behind this term here. And you'll see why in just a second. So that's going to be our in energy, and then we're going to add, we can factor out this negative sign and throw it in here. This is going to be our out. And then we're adding to it our differential change in heat and our change in non-flow work. I'm going to go ahead and abbreviate non-flow as NF for now. Now, knowing the equivalence between internal energy and enthalpy, being that internal energy, or enthalpy rather, is equal to internal energy plus pressure times volume, and we already said that pressure times volume is equal to pressure over density, we can rewrite these two chunks here as enthalpy, or H. And then now we will have H in and H out terms for our flow system. So, doing this, I think we've simplified the equation as much as we really need to here, and I'm just going to go ahead and copy down the entire thing. I'm going to copy down both sides here. So, again, this is going to be our left side. This is just all of our energy equivalences that we've already discussed, and that's going to be equal to, again, our entire right side. So, we can say H now, and this will be our inlet terms here. And then we're going to go ahead and subtract our outlet terms. There we are. And this, right here, is our energy balance. I'm going to go actually ahead and highlight it in blue, because this will be the energy balance that I will be referring to for the rest of this video here. So if I say general energy balance, this is the equation that I am indeed referring to. And this works, again, for really any general flow system, whether or not the liquid is compressible. So there is our general energy balance, and what we need to do now is we want to derive some sort of Bernoulli's equation for our systems as follows. Now from this, we can derive another equation, and we just talked about this, it's Bernoulli's equation. Now, Bernoulli's equation is applied for any flow that is steady, aka its density isn't changing at specific pressure points, as well as we aren't seeing any compression of the fluid, and we aren't seeing any viscous flow forces affecting the fluid's velocity. And so, from this general equation of state here, we can go ahead and attempt to derive Bernoulli's equation. So now that we've gone ahead and derived this energy balance equation, I think we need to next go ahead and derive a subcomponent of this equation, the Bernoulli equation. This energy balance, this more defined energy balance, I guess I could rather say, is going to be more useful for us for incompressible components. something like air at higher temperatures. And to do this, there are going to be a couple of assumptions that we're going to have to make about the system. The first is that it will be some sort of steady state system, or that there will be some sort of equivalence between the mass going into the system and the mass exiting the system. What this means is that the change in mass will be zero. So we can equivocate the left-hand side of this equation here to 0. In doing so, we can then solve this other side of the equation here by moving the term that is multiplied by the differential of mass out of the system and moving that to the left-hand side of the equation, and then dividing the entire equation by the differential of mass itself. Now, I'll write this down more succinctly here. In a steady state system, we know that the derivative of mass entering the system will be equal to the derivative of mass, the differential, rather, of mass leaving the system. Therefore, I'm no longer going to use the subscripts in and out below this general energy balance equation. Now, similarly, when dividing the entire equation by dm and moving this term here to the left side will give us the equation and we are going to need to use the in subscripts on these parts of, and the out subscripts rather, on these parts of the equation in order to differentiate the in velocity and the out velocity. I should rather make this clearer that this is a 2, and there we are. And we divided the entire equation by dm. Again, we took off the subscripts. Now, using kind of the equivalences for enthalpy being equal to internal energy plus the work done on the system, we can write this again as enthalpy plus P over rho, as we did earlier. And by doing this, we are then able to construct an equation similar to this. So let's go ahead and plug all these terms in for the enthalpies. Now, for an incompressible fluid, we will have rho being equal to one another. So we do not need to denote that in or out. And we come out with this equation here. There we are. Now, by moving terms to respective sides of the equation, I'm just going to do addition and subtraction at this point, and we will come up with this equation here. Let's see. We're going to move our pressures next to each other. And we're going to move our terms for potential energy next to one another. Do note that I'll call this line 1 and this line 2. In line 2, I did leave out the kinetic energy term. That should still be equated in there. I just ran out of room. So I'll go ahead and put the kinetic energies next to each other as well. And add potential energies, and equate this then to our difference in internal energy plus differential of heat with respect to mass, and similar for our non-flow work. Now, in Bernoulli's equation, or rather in any sort of thermodynamics concept, this entire term, this change in internal energy plus the differential of heat with respect to mass, is generally referred to as frictional heating, sometimes denoted with this F here. This is frictional heating. So this would be all of the heating that occurs kind of from rubbing, say, the stirrer against the particles of the fluid, or so on. Now, we are going to go ahead and ignore that for Bernoulli's flow equation, as well as we are going to ignore non-flow work. So the only work that is happening is going to be the work from entering and exiting the system. And thus, we come to Bernoulli's equation here, which is this term being set equal to 0. And this is what we call Bernoulli's equation. What's important about this is that it only works for incompressible fluids, in which the density will not change as pressure changes. And we can see that being relevant in this term here. The density is seeming to remain constant throughout the flow of the system. Alright, so from here, I'm going to go ahead and move us into two examples. So now that we've gone ahead and derived these two equations here, let's go ahead and apply them to two scenarios. Now, in order to do this, I'm going to have to set up some sort of scenario here. Let's start with a very simplified scenario of a horizontal pipe. And this pipe will have some sort of water flowing through it, and we will say that the velocity entering the pipe is going to be the velocity out of the pipe. So V in is going to be equal to V out. We can also say, we know the fluid is water, therefore it is incompressible, or rho in will be equal to rho out. We're also going to say that the change that occurs in this pipe is some sort of pressure drop. So let's say we have 900,000 pascals here, and it's going to drop to, well, let's make this a little bit more realistic actually. We want to have a drop of 900,000 pascals in this tank here. So let's say we are going from, I don't know, 10 to the 6th pascals all the way down to, 10 to the 6th minus 10 to the 4th. Let's see, 10 to the 6th. One, two, three, four, five, six. 1, 2, 3, 4, 5, 900,000. Will be 10 to the 5th pascals over here. I'm going to do some real quick addition there to make this problem go ahead and work out for us. So we're having a drop of 900,000 pascals, and that's the important part here. We can also say that the change in z is going to be 0, and that would be some unit of length, because the pipe is indeed horizontal. Now, the other thing that I'm going to stipulate here is that we have some sort of steady state interaction happening, or that the mass going into the system is equal to the mass exiting the system here. Now, finally, the last stipulation I'm going to place here is that we have no heat being added. Actually, Rather, I'm going to say there's going to be no non-flow work. On the system here. And with that, we can go ahead and write our equation here. So I'm going to go ahead and copy this down. There we are. And we're going to go ahead and write this equation here. Now, there's a couple cancellations we can make immediately. We already said no non-flow work. And we have also said that the change in mass on this side here is going to be equal to 0, which will cancel out this entire side of the equation. And then finally, if there is no heat being added to the system, which we see no heat being added, I'll add that as another assumption. Let's title this Assumptions. These assumptions are present based on the diagram that was drawn. So if we have no non-flow work and no added heat, we can cancel out this added heat term as well. So what we are going to have is some equivalence here. And technically this would be out, 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 and this would be in, in. Now, some quick cancellations, we will basically be able to determine that the enthalpy entering the system is going to be equal to the enthalpy exiting the system. And we defined enthalpy earlier as internal energy plus the work being done on the system. And we wrote that earlier as pressure over density. Now the density of our substance is water, and water being a liquid is incompressible, which means that the density will remain constant across the pressure drop. Therefore, we can write that pressure in minus pressure out over rho, or our density, will be equal to our change in internal energy here. And we'd already written that internal energy is equal to specific heat at a specific volume times temperature, meaning that we can equate this to specific heat at a volume multiplied by the final temperature, or the temperature out, rather, minus the in temperature. And what this means is that now we have some sort of relation between the changing pressure and actually changing the temperature of our water. So in this case, we could go ahead and plug and chug all of these numbers here and come out with some idea of the change in temperature of our water. Now we said that the change in pressure was, I believe, 900,000 pascals. And the density of water is usually tabulated at about 1,000 kilograms per meter cubed, I believe. And then we can go ahead and divide that by its specific heat per unit volume. I do not have that memorized for water off the top of my head, so I would have to go and look it up. Specific heat per volume, unit volume of water. And I'm just going to type that into Google. Yes. Alright. So that would be 4.186 joules per gram joules per kilogram Kelvin is what we're looking for. So it's about 4.184 joules, which is a number that I probably should have had memorized from regular chemistry class. So let's go ahead and pull this back up here. Alright. 4184 joules here. Alright, 4184. And with this, we could go ahead and plug that into some sort of calculator. Let's see. And plugging these numbers into some sort of calculator, as you can see here is my calculator for random things. Let's see, we had 900,000 divided by 1,000 divided by 4184, and we are given that the pressure will, or the temperature rather, will change by about 0.25 degrees Kelvin by keeping our units consistent here. And that makes sense. We wouldn't expect a drastic change in pressure to drastically change our water temperature. However, this is still going to change the temperature to some extent, which isn't something that is always intuitively present to a non-chemical engineer. Now, let's go ahead and talk through another example here. And in this example, what I think is most interesting to discuss is attempting to find the velocity of air as it flies from a tank from some hole. So I'll go ahead and draw some tank here. And in this tank, we're just going to have normal air. And here is the hole in which it is flowing out at some speed. So I'm going to give an initial pressure of 10 to the 4th pascals inside this tank, and I'll say 0 pascals is the pressure outside of the tank. Now, we can go ahead and use Bernoulli's equation in order to attempt to define the velocity of air in, at, or around the hole, the velocity of air as it leaves the tank. And so let's go ahead and write Bernoulli's equation again. It's going to be P in minus P out over the density of the substance. Remember, Bernoulli's equation only works for an incompressible substance. Air at low temperatures will work here. And we're going to add to that the basically change in velocity squared, velocity in squared plus velocity out squared over, or not plus, rather minus, over 2. And finally adding to that g times z in minus z out. And again, all of that is equal to 0. So, we can say that the velocity inside the tank, or V in, is going to be 0 meters per second. And because we can take that at any point within the tank. So I'll go ahead and take it at that point there. At that point, the air isn't particularly moving at a particularly fast rate. So we can go ahead and cancel out either V in or V out. I'll cancel out V in. And we can also say that because there is only one hole, we do not need to take into account the change in height, so we can cancel that out as well. So what we are really looking at now is the change in pressures, which we have already said is 10 to the 4th pascals, over rho of air plus V out squared over 2 is going to be equal to 0, right? Technically, it doesn't matter whether or not you have this sign as plus or minus, because that will cancel itself out algebraically anyway. Now, what we need to solve for here is the rho, or the density of air. To do that, we already know that air has about 0.029 kilograms per mole, is about its molecular weight. And so what we need to do to that then is apply the ideal gas law to find the volume of air. At atmospheric pressure, we know it's 101,325. So I'm just going to do 1 over volume equals P over RT. And so we can divide that then by 8.314 and multiply that then again by a temperature. Usually atmospheric temperature is about 298 Kelvin, joules per mole Kelvin here, and this would be in pascals. So when we go ahead and run that there, we get about, I believe, 1.2 kilograms per mole is about the density of air. And so we can plug that in right here. Now, let's go ahead and solve for the velocity. So, solving for velocity, we are going to have, technically this should be a negative sign, I believe, so that we can have 10 to the 4th over 1.2 times 2 rooted will be our velocity out. And here is the expression I'm going to go ahead and plug into my calculator here. Let's do this. So np dot square root 2 times 10 to the 4th power over 2. And when that comes out to about, oh, I may not have ran import numpy as np. So let's try and run that again. It's not going to like me. About 100. About 100. Oh, I didn't divide by 1.2 as our density, which should give us, yes, about 129, 129 meters per second here, which will be about 129 meters per second here, which is indeed very, very fast. I believe that equivocates to about 288 miles per hour. So we have very fast speeds for a relatively low, actually, difference in pressure. That's less than an atmospheric difference in pressure. So in this video we went through the derivation for Bernoulli's equation from the generic energy balance equation, and then we applied it to two examples, one of air leaving a tank and one of water flowing through some sort of horizontal pipe. I hope this was helpful. Thank you.